As requested by Anna, it's time for our revision video all about kinetic theory and gases. In this revision video, I am going to model a particular technique for revision of mind mapping. I'm going to build a mind map of the whole of the gases topic. The particles of a gas are zooming about in all directions. They have lots and lots of energy, lots of kinetic energy. If you confine a gas into a space, then those particles that are zooming about everywhere in all directions randomly start colliding with the walls of that container. When a particle is hitting the side of the container, that's a force on an area. So there's pressure inside the container from the gas that's trapped within there. The gas tries to take up as much space as available to it as its particles zoom around in all directions. So gases have lots and lots of energy. They're particles, loads of kinetic energy. But if we cool the gas down, we get less and less kinetic energy of those particles. If we keep cooling a gas down right until it has no kinetic energy, we reach something called absolute zero. And that's where this guy comes in, Kelvin. Because absolute zero is minus 273 degrees Celsius, we have a new temperature scale in this unit, the Kelvin scale. 0 Kelvin is at minus 273 degrees Celsius at absolute zero. And then any temperatures that we have in degrees Celsius, we can convert into Kelvin easily by simply adding on 273. In this unit, temperature is in Kelvin. So branch 1 of my mind map here is showing the idea of solids, liquids and gases, the movement of particles. The idea that at absolute zero the particles have stopped moving. That temperature is minus 273 degrees Celsius or 0 Kelvin. And we can convert between Celsius and Kelvin by adding on 273 to degrees Celsius to turn it into Kelvin units. Now this unit is all about medical physics, so it's likely that when we talk about gases, it's going to be linked to medical bottled gas. Bottles of oxygen can be stored at the hospital. They can be stored in an ambulance, for example, and transported from place to place. So the second branch of my mind map here is all about bottled gases. Oxygen gas could be transported, hence the picture of the car, or stored, hence the picture of a door. In these bottles, the gas is at high pressure. Loads of gas has been squashed into that small volume. So high pressure, low volume. By having a low volume, we can make smaller bottles to transport lots of oxygen in less space. But the danger of that is as the bottles get hotter, we could increase the pressure even more and cause the bottles to explode. So we have to consider how we transport them and where they're stored. It's really important in mathematical questions about bottled gases to also remember that the volume of the bottle will need to be taken away at the end of a calculation. Once the gas is allowed to escape, and once the gas has filled the bottle at atmospheric pressure, then no more gas will leave the bottle. The bottle will never be completely empty. And so there is a relationship between the kinetic energy I was talking about in the first branch and the temperature of the gas that's trapped in the bottle I was talking about in the second branch of my mind map. Temperature and kinetic energy are directly proportional to one another as long as the temperature is in Kelvin. Kinetic energy is a half of the mass times the velocity squared. As you increase the kinetic energy of the particles, you're increasing the speed of the particles. As you warm a gas, as you heat it up, you're transferring more kinetic energy to it. If you're transferring more kinetic energy to it, you're increasing the speed of the particles. As you double the temperature in Kelvin, you are doubling the amount of kinetic energy that the particles have. And so as my mind map is building up, we move to the gas laws. First we're going to think about Charles's law, hence the big ears at the top there, and we're going to think about Boyle's law. I don't know why I drew a boil under someone's arm, it's just what came to me. So Charles's law. Using this equipment, we keep the atmospheric pressure as a constant pressure through the experiment. By trapping the gas here, we are keeping the mass of the gas constant through the experiment. But by changing the temperature within this water bath that's been created, we're changing the temperature of that trapped gas. And as the temperature changes, we can measure the volume of the trapped gas. The relationship discovered by this type of apparatus shows us that as the temperature in Kelvin increases, the volume increases too, and they are directly proportional to one another. As you heat up a gas and give its particles more energy, it wants to move more. But if it has to hit the sides exactly the same rate, so we keep the pressure the same, which is what's being done here, the only way those particles, as they're moving round faster, will only hit the sides the same will be if they're moving round in a bigger space. So as you heat the gas, the volume gets bigger. Now Boyle's law is also looking at measuring the volume of a gas, and you could use this equipment or this equipment. In both those pieces of equipment, we're changing the pressure, measuring the volume, so the temperature has to stay fixed, as well as the mass of gas not changing. The results of this experiment show us that if you times together the pressure and the volume at any particular reading, you always get the same value. That shows there must be an inversely proportional relationship going on. As gases are squashed into smaller and smaller spaces, the particles are colliding with the walls more and more force on an area, more pressure. So as the volume gets smaller, the pressure increases. Pressure and volume are inversely proportional to one another. So both Charles's law and Boyle's law investigate what happens with a changing volume. In Charles's law, we find that temperature and volume are directly proportional as long as pressure and mass of the gas are fixed. And in Boyle's law, we find that pressure and volume are inversely proportional as long as temperature and mass of the gas are fixed. So we're into the final gas law. Our new branch is telling us all about the pressure law. This time the things we're fixing, sticking in place with our glue, are the volume and the mass. So the volume of the gas mustn't change in this experiment, and the mass of the gas has to stay fixed. No particles in, no particles out. Here, this law is investigating the relationship between the temperature, in Kelvin of course, and the pressure of a gas. So, if we warm a gas and measure its pressure, as the temperature increases, the pressure will increase too. This straight line is showing us, with the temperature in degrees Celsius, that as the temperature gets hotter, the pressure also increases. But it's important where this would trace back and cut the x-axis. The only place where there is zero pressure is the place when the particles are not moving at all. That, of course, is absolute zero. So if the graph is plotted in degrees Celsius, we can trace that line back and prove that absolute zero is at minus 273 degrees Celsius. This equipment would help us get the results for our graph. We have a fixed volume of gas because of the test tube, a fixed mass of gas that's trapped in our test tube. We can change the temperature of the gas by putting different things into our beaker like ice or boiling water, and measure the pressure using the pressure sensor. We would find that the pressure is directly proportional to the temperature in Kelvin. If the temperature is in Kelvin, as we increase the temperature, we give more energy to the particles. If we give the particles more energy, then they start moving faster. When they move faster, they start hitting the sides of the container more, so there's more force on the area, there's more pressure. As temperature in Kelvin increases, the pressure increases directly proportionally. We're at the last branch of my mind map because, of course, all these gas laws build to an equation. We had Charles's law, Boyle's law and the pressure law, and together the relationships build the gas equation. So from Charles's law we have V1 divided by T1 is equal to V2 divided by T2. From Boyle's law, we have P1 times V1 is equal to P2 times V2. And from the pressure law, we have that P1 divided by T1 is equal to P2 divided by T2. All the ones are before, all the twos are after. So the pressure times the volume of a gas before divided by its temperature in Kelvin before is always going to give you the same number as the pressure times the volume afterwards divided by the temperature in Kelvin afterwards. The important thing with the equations is to remember to keep that temperature in Kelvin. Remember those units. Show your working out and use your triangles if you need to once you've got it down to just 3 numbers, 2 numbers and a letter. Make sure that if in the question any of the variables are kept constant, for example a tube is open to atmospheric pressure and pressure isn't changing, you can cancel those out and make the equation simpler by taking it from a 6-parter to only 4 parts. And so that's it. That's gases, the whole topic in one video and one mind map. All the ideas on one A4 piece of paper.
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.